Docker is a powerful platform that simplifies building, shipping, and running applications using container technology. It packages applications with all their dependencies into standardized units called containers that can run anywhere. Before Docker, developers faced several challenges. The infamous, "it works on my machine" problem occurred when code worked in development but failed in production due to environment differences. Managing dependencies across different systems was complex. Scaling applications was difficult, and traditional virtual machines wasted significant resources. Docker solves these problems through containerization. Containers package an application with all its dependencies into a single, lightweight, executable unit that can run consistently across different computing environments. A Docker container includes the application code, runtime, system tools, libraries, and settings, everything needed to run the application. Unlike virtual machines, containers share the host OS kernel and isolate the application processes from the system. To understand Docker's advantages, let's compare its architecture with traditional virtual machines. This comparison will highlight why containers are more lightweight and efficient. In traditional virtualization, each virtual machine runs its own complete operating system on top of a hypervisor. This means significant overhead from running multiple OS instances and slower startup times. With Docker, containers share the host operating system kernel through the Docker engine. Each container includes just the application and its dependencies, making them much lighter and faster to start than virtual machines. The key differences are clear. Virtual machines are heavy, requiring a full OS for each instance, resulting in slow boot times and significant resource overhead. Docker containers are lightweight, sharing the host OS kernel, which means faster startup times and more efficient resource utilization. This makes Docker ideal for modern microservices architectures and cloud-native applications. Let's explore the architecture of Docker. The popular containerization platform, Docker follows a client-server architecture with several key components that work together to build, ship, and run containers efficiently. The Docker client is the command line interface that users interact with. When you run commands like docker run or docker build, you are using the Docker client. It sends these commands to the Docker daemon, which does the actual work. The Docker host is the environment where your containers run. It contains the Docker daemon, images, containers, networks, and storage. The host can be your local machine or a remote server. The Docker daemon is the brain of Docker. It's a persistent background process that manages Docker objects like images, containers, networks, and volumes. The daemon listens for Docker API requests and processes them. Docker images are read-only templates used to create containers. They contain the application code, libraries, dependencies, and other files needed to run an application. Images are built from Docker files and can be stored locally or in registries. Containers are runnable instances of Docker images. They are isolated, lightweight, and portable environments where applications run. Each container has its own file system, networking, and isolated process space. Docker registries are repositories for Docker images. The most popular public registry is Docker Hub, but you can also use private registries. Registries allow you to store, share, and distribute Docker images across different environments. Now let's see how these components interact. When you run a Docker command, the client sends it to the daemon. If the daemon needs an image it doesn't have locally, it will pull it from a registry. Let's walk through a typical workflow. When you run, Docker run nginx. First the client sends this command to the daemon. The daemon checks if it has the nginx image locally. If not, it downloads it from Docker Hub. Then it creates a container from the image and starts it. This entire process happens seamlessly behind the scenes. This is the fundamental architecture of Docker. Understanding these components and how they interact helps you work more effectively with Docker and troubleshoot issues when they arise. Thank you for watching. In this tutorial, we'll walk through the process of installing Docker on your system. Docker provides easy-to-follow installation guides for all major operating systems. First, you'll need to select the appropriate installation method for your operating system. Docker supports Windows, Mac OS, and Linux platforms. For Windows users, Docker Desktop provides an all-in-one solution. Make sure your system meets the WSL2 or Hyper-V requirements. Mac users can install Docker Desktop for Mac, which works on both Intel and Apple Silicon chips. Linux users have distribution-specific packages available, though many prefer Docker's repository for easier updates. The installation process follows these general steps, though details may vary by operating system. First, visit docker.com/get-started to download the appropriate version for your system. Download Docker Desktop for Windows or Mac, or the appropriate package for your Linux distribution. Run the installer. On Windows and Mac, this will be an executable file, while Linux may use package managers like apt or yum. Follow the setup wizard instructions. The default options are usually fine for most users. You'll typically need to restart your system to complete the installation. Finally, verify your installation works correctly using the command line. After installation, let's verify Docker is working properly. Open your terminal or command prompt and run these commands. First, check your Docker version with docker -- version. This should display the installed Docker version, confirming the CLI tools are working. Next, run the Hello World container to test Docker's ability to pull and run images. This will download a test image and display a welcome message if everything is working. Congratulations! You've successfully installed Docker. You are now ready to start containerizing your applications. One of the most fundamental concepts in Docker is understanding the difference between images and containers. These are the building blocks of Docker's architecture. A Docker image is a read-only template that contains the instructions for creating a container. It's like a blueprint or a snapshot of what your container should look like. Images are built in layers. Each layer represents an instruction in the Docker file. The base layer typically contains the operating system, followed by runtime environments, your application code, and finally configuration settings. A container is a runnable instance of an image, while the image is the blueprint. The container is the actual running process based on that blueprint. When we run a container, Docker creates a writable layer on top of the image layers. This is where your running application lives, isolated from other containers. You create a container from an image using the docker run command. A single image can be used to create multiple containers, each running independently. To summarize the key differences, images are immutable templates while containers are the running instances. Images are stored on disk, while containers consume memory and CPU. And importantly, you can create multiple containers from a single image. This distinction between images and containers is fundamental to working effectively with Docker. Images provide consistency and reproducibility, while containers provide isolation and portability. Let's explore the essential Docker commands you'll use daily when working with containers. These commands form the foundation of container management with Docker. First, you'll need to pull images from a registry. The Docker pull command downloads an image from Docker Hub or your configured registry. Here we are pulling the nginx web server image. To see all images available on your system, use Docker images. This shows the repository, tag, image ID, creation date, and size of each locally stored image. The Docker run command creates and starts a container from an image. The P flag publishes container ports to the host. Here we are mapping port 80 in the container to port 80 on our host machine. Docker PS shows you're currently running containers. Add the A flag to see all containers, including stopped ones. This is useful for checking container statuses and finding container IDs. To gracefully stop a running container, use Docker stop with the container ID or name. This sends a SIGTERM signal allowing the container to shut down properly. After stopping a container, you can remove it with Docker room to free up space. Remember that containers are ephemeral. You can always create new ones from your images. These commands represent the basic workflow of working with Docker containers. From pulling images to managing running containers. Mastering these commands will give you solid foundation in Docker operations. Let's explore how to create a Docker file, which is a text document containing all the commands needed to assemble a Docker image. The Docker file serves as a blueprint for building containerized applications. Here's a basic Docker file for a Node.js application. Let's go through each instruction one by one to understand what it does. From specifies the base image we are building upon, in this case Node.js version 16 on Alpine Linux. WORKDIR sets the working directory inside the container to app. Copy copies the package, JSON and package lock, JSON files into the container. Run executes npm install to install all dependencies. Copy now copies the rest of the application code into the container. Expose documents that the container listens on port 3000 at runtime. CMD specifies the command to run when the container starts. Now that we have our Docker file ready, let's see how to build an image from it. We use the docker build command to create an image from our Docker file. The T flag tags our image with a name and version, and the dot specifies the build context. Docker builds images in layers, with each instruction in the Docker file creating a new layer. This layered approach makes builds efficient through caching. Building layer 1, from. Building layer 2, WORKDIR. Building layer 3, copy. Building layer 4, run. Building layer 5, copy. Building layer 6, expose. Building layer 7, CMD. And that's how we create and build a Docker file. Each layer represents an immutable change to the file system, making containers lightweight and efficient. Let's examine some of the most commonly used Docker file instructions and what they do. From specifies the parent image for your build. It should be the first instruction in your Docker file. WORKDIR sets the working directory for any run. CMD. ENTRYPOINT. Copy and ADD instructions that follow. Copy copies files or directories from the host into the container's file system. Run executes commands in a new layer on top of the current image and commits the results. Expose informs Docker that the container listens on the specified network ports at runtime. CMD provides defaults for an executing container. There can only be one CMD in a Docker file. env sets environment variables that will be available to all subsequent instructions and in a running container. Volume creates a mount point and marks it as holding externally mounted volumes. These are the fundamental Docker file instructions you'll use most often when creating Docker images. Understanding these commands is key to building efficient and secure containers. Let's explore Docker networking, which enables communication between containers and between containers and the host system. Docker provides several networking options to suit different use cases. This represents a host machine, which could be your laptop, server, or cloud instance running the Docker engine. Inside Docker, we can create virtual networks that containers can join. These networks provide isolation and secure communication channels between containers. Here we have two containers: a web application running on port 3000 and a database running on port 5432. These containers need to communicate with each other. Port mapping allows us to expose container ports to the host system. Here we are mapping host port 8080 to the container's port 3000, making the web app accessible from outside. The containers can communicate directly through the Docker network, while external access is provided through port mapping. Here are the essential Docker commands for networking. First, we create a network, then run containers attached to that network. The P flag enables port mapping. Docker networking provides flexible options for container communication while maintaining security and isolation between services. Now let's examine Docker volumes, which solve the critical problem of data persistence in containers. By default, container file systems are ephemeral. They disappear when the container stops. This is the fundamental problem we need to solve. When a container is destroyed, all its internal data is lost unless we specifically save it. Here we see the container lifecycle: created, running, and eventually destroyed. Any data stored in the container's file system is lost when the container is removed. The solution is Docker volumes, which provide persistent storage that exists independently of any container's lifecycle. Volumes store data on the host file system, outside the container's isolated environment. This represents a Docker volume, which is a managed storage location that Docker maintains for us. Here's our container, which will have access to the persistent volume. The volume is mounted to a specific path inside the container, in this case, data. The volume connection ensures data written to data in the container is actually stored persistently on the host file system. These are the key Docker commands for working with volumes. We can create named volumes that Docker manages, or use bind mounts to connect specific host directories. Volumes are essential for databases, configuration files, and any data that needs to persist between container restarts or survive container removal. Let's explore Docker Compose, a powerful tool for defining and running multi-container Docker applications. With Compose, you can configure all your application's services in a single file and spin them up with a single command. When working with multiple containers, managing them individually with Docker run commands becomes complex. Each container needs proper networking, environment variables, and dependencies configured correctly. Here we see the typical approach using individual Docker run commands. We need to manually create each container, set up networking between them, and manage their life cycles separately. This quickly becomes unwieldy. Docker Compose solves this problem by allowing us to define a multi-container application in a single YAML file. This file describes all the services, networks, and volumes needed for our application. The version specifies which Compose file format we're using. Under Services, we define all our containers. First service is a web server using nginx. We map port 80 from host to container. The web service depends on our app service. The app service will be built from current directory. We set environment variables for the app. Database service using Postgres image. We configure the database with environment variables. This single configuration file replaces all those complex Docker run commands. The relationships between services are clearly defined, and the entire application can be managed as one unit. Now let's look at the essential Docker Compose commands for managing your application. This starts all services defined in the Compose file in detached mode. Lists all services and their status, similar to Docker PS but for Compose. Shows aggregated logs from all services. Add F to follow logs. Stops and removes all containers, networks, and volumes. Scales the web service to run 3 instances. Docker Compose dramatically simplifies multi-container application management. It's perfect for development environments, CI/CD pipelines, and local testing of complex systems. Let's explore some of the most valuable real-world use cases for Docker that demonstrate why it has become such an essential tool in modern software development and deployment. First, let's look at microservices architecture. Docker is perfectly suited for building and deploying microservices, where applications are composed of small, independent services that communicate over well-defined APIs. In this typical microservices setup, we have an API gateway that routes requests to various independent services. Each service runs in its own container. The API gateway connects to each microservice, which can be developed, deployed, and scaled independently. Docker makes this architecture practical by providing lightweight isolation for each service. Another powerful use case is in continuous integration and continuous deployment pipelines. Docker ensures consistency across all stages of the pipeline from development to production. Here's a typical CI/CD pipeline. First, code is committed to version control. Then a Docker image is built containing the application and its dependencies. The built image is then used to run tests in an environment identical to production. After passing tests, the same image is deployed first to staging, then to production. The key benefits of using Docker in CI/CD include consistent environments across all stages, faster deployments since we are shipping pre-built images, easy rollbacks by simply redeploying previous images, and the ability to scale testing by spinning up multiple identical test environments. Finally, let's examine how Docker revolutionizes development environments by eliminating the "works on my machine" problem and making onboarding new developers dramatically easier. Before Docker, development environments were plagued with problems, the infamous "works on my machine" issue. Complex setup documentation, version conflicts between different projects, and environments that would drift over time as configurations changed. With Docker, developers simply run Docker Compose up to get a complete development environment. Everyone gets identical environments. Dependencies are perfectly isolated between projects, and onboarding new team members becomes trivial. The setup process becomes incredibly simple. New developers just need to clone the repository and run Docker Compose up. That's it. The exact same environment that runs in production can now run on every developer's machine. Security is a critical consideration when working with Docker containers. While containers provide isolation, misconfigurations can lead to vulnerabilities. Let's explore key security considerations and best practices. First, let's examine common security concerns when using Docker containers. On the left we have common security risks, and on the right their corresponding best practice solutions. Privileged containers can be dangerous. so we should run as non-root users. Image vulnerabilities should be addressed with regular scanning. Network exposure should be minimized to only required ports. Now let's look at Docker file security best practices through a comparison of poor and secure implementations. Here we compare two Docker files. The bad example on the left uses the latest tag, which can be dangerous. Doesn't clean up package lists and runs as root. The good example on the right uses a specific version tag, combines commands to minimize layers, cleans up package lists, copies only requirements first for better caching, and runs as a non-root user. Let's summarize the key Docker best practices across different aspects of container lifecycle management. First, build practices. Building construction build. Always specify exact version tags for base images. Use multi-stage builds to reduce final image size. Combine commands to minimize the number of layers. Exclude unnecessary files with Docker ignore. First, build practices, rocket deploy. Implement health checks for container monitoring. Set CPU and memory limits for containers. Use environment variables for configuration. Configure proper logging for observability. Next, log security practices. Always run containers as non-root users. Regularly scan images for vulnerabilities. Follow principle of least privilege. Use Docker secrets for sensitive data. Next, bar graph monitor practices. Collect container metrics for analysis. Aggregate logs centrally for debugging. Monitor container performance metrics. Set up alerts for critical issues. Following these Docker best practices will help you build secure, efficient, and maintainable containerized applications. Remember to regularly review and update your practices as Docker evolves. Running Docker in production presents unique challenges that require careful planning and the right tools. Let's explore the key considerations for production-grade container deployments. Production deployments face several key challenges. Container orchestration for managing multiple containers. Scaling to handle varying loads. Monitoring for observability. Security hardening. And persistent data management. Container orchestration tools help manage the deployment, scaling, and networking of containerized applications. The two main options are Kubernetes and Docker Swarm. Kubernetes is the industry standard with advanced features but a steeper learning curve. Docker Swarm is simpler to set up but has fewer features, making it better for smaller deployments. A robust production pipeline typically includes development, testing, staging, and production environments to ensure quality before release. Code progresses through development, testing, staging, and finally production. Each environment should mirror the others as closely as possible. Several deployment strategies help minimize risk. Blue-green maintains two identical environments. Rolling updates gradually replace instances. Canary releases test with a small percentage of users. And A/B testing compares different versions. Monitoring containerized applications is essential for maintaining reliability and performance. Let's examine the key components of a Docker monitoring stack. A complete monitoring stack typically includes several specialized tools working together. Prometheus collects and stores time series metrics from containers and hosts. Grafana provides dashboards to visualize the metrics collected by Prometheus. Elasticsearch, Logstash and Kibana help aggregate and analyze container logs. Jaeger tracks requests as they flow through microservices for performance analysis. Several key metrics provide insight
CPU
into
and
container
memory
health
use
and
and
indicate
performance.
resource constraints and potential bottlenecks. Network traffic shows communication patterns between services. Disk I/O metrics reveal storage performance issues. Container restarts may indicate crashes or health check failures. Response times help identify performance degradation. Error rates track the stability of your services. The Docker ecosystem is rich with tools and services that extend Docker's capabilities. Let's explore the core components and extended ecosystem that make Docker so powerful. At the heart of Docker are three core components that provide the foundation for containerization. Docker Hub is the world's largest container registry, containing millions of public images and providing private repositories for teams. Docker Desktop provides an easy-to-use GUI for managing containers on Windows and Mac. With built-in Kubernetes support, Docker Engine is the core runtime that builds and runs containers using containerd and runc under the hood. Beyond the core components, a rich ecosystem provides a user-friendly web interface for managing containers. Watchtower automatically updates running containers to their latest versions. Falco monitors container behavior for security threats and anomalies. Cadvisor collects and exports container resource usage metrics. Dive helps analyze Docker image contents and layer efficiency. The container ecosystem continues to evolve with several exciting trends, even faster startup times and smaller footprints. Security-focused runtimes like gvisor and Kata provide stronger isolation. Tools for managing containers across multiple cloud providers are evolving rapidly. Containers optimized for AI, milliliter workloads with GPU support are becoming standard. Serverless container platforms abstract away infrastructure management. ARM64 support enables Docker on edge devices and new hardware platforms. Let's walk through a complete Docker demonstration where we'll containerize a full stack application with React frontend, Node.js backend, and PostgreSQL database. We'll build a typical three-tier application architecture with separate services for frontend, backend, and database. Our architecture consists of a React frontend that talks to a Node.js API, which in turn connects to a PostgreSQL database. Each component will run in its own container. Here's our step-by-step Docker files for each service to define their container images. Next, we'll create a Docker Compose file to orchestrate all services together. We'll configure networking between services and persistent volumes for the database. Then we'll build the images and start all containers with a single command. Finally, we'll test the application and debug any issues that arise. Here's our complete Docker Compose file that ties everything together. We're using version 3.8 of the Compose file format. Under Services, we define our three containers. The front-end service will be built from the front-end directory. We expose port 3000 for the React development server. The front-end depends on the back-end being available. The back-end service is built from the back-end directory. We expose port 5000 for the API server. We set environment variables including the database host. The backend depends on the database service. We use the official PostgreSQL 13 image for our database. We configure database credentials through environment variables. Most importantly, we create a volume for persistent data storage. Finally, we declare our named volume for the database. Now let's run our application and see it in action. We start all services in detached mode with Docker Compose upd. Docker creates a default network for our application. It also creates a volume for our database persistence. The database container starts successfully. followed by the backend API container, and finally our front-end container. We check the status of our services with Docker Compose PS. This shows all our running containers. The database is running internally on port 5432. Our backend is exposed on port 5000. And our front-end is available on port 3000. Success! Our full-stack application is now running in Docker containers, with all components properly connected and communicating. Even with Docker's advantages, you'll inevitably encounter issues. Let's look at some common problems and how to solve them. Here are some of the most frequent Docker problems and their solutions. Port conflicts happen when multiple services try to use the same port. The solution is to either change your port mapping or stop the conflicting service. Docker can consume significant disk space. The prune command removes stopped containers, unused networks, and dangling images. Permission errors often occur when your user isn't in the Docker group. This command adds your user to the group, though you'll need to log out and back in. Continuous restarts usually indicate a crashing application. Checking the logs is the first step to diagnose the problem. Docker provides several container logs to help diagnose application output and errors. Execute commands in a running container for debugging purposes. Monitor real-time CPU, memory, and network usage of containers. Get detailed low-level information about Docker objects. Check how much disk space Docker is using for images, containers, and volumes. Remove unused data to free up disk space. Now let's explore some advanced Docker concepts that can help optimize your container workflows and improve build performance. Multi-stage builds are a powerful Docker feature that helps create smaller, more secure final images by separating build time dependencies from runtime. In traditional single-stage builds, the final image contains everything: source code, build tools, dependencies, and the runtime environment, resulting in unnecessarily large images. Multi-stage builds use multiple from statements. The first stage contains all build tools and compiles the application. The final stage copies only the compiled artifacts, leaving behind unnecessary build dependencies. The
Smaller
benefits
images
of
mean
multi-stage
faster
builds are
downloads and
reduced storage requirements. Fewer components mean fewer potential vulnerabilities in production. Smaller images deploy faster, especially important in scaling scenarios. BuildKit is Docker's next-generation build system with significant performance improvements and new features. BuildKit introduces several powerful features when possible. More efficient caching reduces unnecessary rebuilds. Secure secret management during builds without leaving traces in final image. Improved build output and error messages for debugging. Overall faster build times compared to traditional builder. To use BuildKit, enable it through environment variables. The progress flag controls the verbosity of build output. Docker registries are essential for storing and distributing container images. Let's explore the different registry options and how to work with them. There are several types of Docker registries available, both public and private. Docker Hub is the default public registry that anyone can access. GitHub Packages provides integrated container registry with your code. Google Container Registry offers secure, private Docker storage on GCP. For proprietary software, organizations typically run private registries like Docker Trusted Registry or open source solutions like Harbor. The typical image workflow involves building locally, tagging for your registry, pushing to the registry, then pulling and running on target systems. Here are the essential commands for working with Docker registries. Build an image from Docker file in current directory and tag it. Tag an existing image with a registry prefix for pushing. Upload the image to the specified registry. Download an image from the registry to another machine. Show all images available locally. Delete an image from local storage to free up space. Congratulations on completing your Docker mastery journey. Let's recap everything you've learned and celebrate your achievement. You've come a long way in your Docker learning path. From complete beginner to Docker master. You've completed 100% of this Docker mastery course, gaining comprehensive knowledge of container technology. Here are all the valuable Docker skills you've acquired, concepts and how it works under the hood. You can manage containers and images like a pro. You can write efficient Docker files to build optimized images. You know how to configure networking and persistent storage. You can orchestrate multiple containers with Docker Compose. You've learned critical security practices for containers. You're ready to deploy containers in production environments. You can monitor and troubleshoot containerized applications. Your Docker learning doesn't stop here. Let me share some excellent resources to continue expanding your containerization knowledge. Here are some recommended resources to deepen your Docker expertise. The official Docker documentation is always the most reliable source. The main Docker documentation portal covers all features. Specialized docs for working with multi-container applications. Documentation for working with Docker's public image registry. Connect with the vibrant Docker community. Official forums for Docker questions and discussions. Search for existing solutions or ask new questions. An active community of Docker enthusiasts. Hands-on projects to reinforce your learning. Take apps you've built and containerize them. Practice breaking applications into microservices. Automate your container builds and deployments. Try deploying containers to AWS, GCP or Azure. Now that you've mastered Docker fundamentals, here's a recommended learning path to continue your containerization journey. Follow this step-by-step path to become a true containerization expert. First, solidify your Docker CLI skills through daily practice. Then apply your knowledge by containerizing real applications. Next, learn Kubernetes for managing containers in production. Expand to cloud platforms that specialize in container hosting. Finally, dive into advanced topics for professional use. Remember that every expert was once a beginner just like you. The key to mastery is consistent practice and continuous learning. Keep building containerized applications and your skills will grow.